Doncs ens fa il·lusió de presentar avui aquesta conferència organitzada per la Societat Catalana de Física de l'Adrian Bachtold, que és professor d'investigació a l'Institut ICFO, l'Institut de Ciències Fotòniques, i va fer la seva tesi doctoral a Basel. Després va estar com a postdoc a diferents llocs, com Berkeley i Delft, i després va ser contractat com a investigador el 2001 a l'Escola Normal Superior de París i el 2005 es va incorporar a Barcelona, primer a l'Institut de Nanociència i Nanotecnologia, el 2005, i després, al cap de pocs anys, ha format part de l'ICFO com a professor de recerca i dirigeix un grup de recerca a l'ICFO. Doncs li deixem la paraula i tenim present que els que seguiu la xerrada des de lluny també després podeu posar preguntes si us ve de gust. Gràcies.
Muchas gracias, estoy contenta de estar aquí. Parlaré en inglés, porque mi catalán es not super top. So I will speak about mechanical vibrations that are nonlinear when they are in the quantum regime. And I will explain you how it is possible to create strong linearities, mechanical nonlinearities so I will explain you how it's possible to create strong mechanical nonlinearities by coupling the vibration of a carbon nanotube with a double quantum dot that is shown by these two balls that are delocalized along the nanotube. And this electromechanical system is read out with a superconducting resonator that is shown behind. So the question that I want to ask here in this presentation is whether it's possible to have nonlinear vibrations in the quantum regime. So in other words, is it possible to have energy levels that are not equally spaced when you work with only a few mechanical quanta, or you can also call these phonons? And such a system would behave completely differently from what we know. So there are a lot of echoes. So I don't know whether I should. So now he says that it should be better. Okay, so and such a system that is shown here would be behaving completely differently from what we know. For example, if we drive the system at frequency omega here, the system will climb from the 0 phonon state to the 1 phonon state, but it will not be able to go to the 2 phonon state because the energy difference here between these two states is different from the quantum h bar omega. What you expect to have are Rabi oscillations where the system will periodically oscillate between the 0 and the 1 phonon state. And obviously this is completely different from what we know with mechanical resonators. So if you take, also at home, so what happens when you drive a resonator, it will, and you drive at, let's say, at frequency omega, it will climb this ladder of, so if you drive at frequency omega, then the system will climb this ladder of energy to a very high number of quanta. And this is because the energy levels here are equally spaced to a very good approximation. And so do you see that here this behavior is completely different from here. So it's fundamentally different. So one way to create strong nonlinearities is to couple mechanical vibrations to a qubit, which is the most nonlinear system that can exist. And in fact, several types of mechanical resonators have been coupled to some superconducting qubits, and they could demonstrate stronger nonlinearities in the vibrations, but it was still relatively weak, so no sign of nonlinearities near the quantum regime, so until very recently. So our goal is to use the vibration of a carbon nanotube that are coupled to a double quantum dot that is shown in red, and where we have one electron that is delocalized between these two dots. And the mechanical vibrations modulate the electron distribution between the left dot and the right dot because of the capacitive coupling between the nanotube and the gate electrodes. If you have questions, please ask us. So I'm happy if you have questions. And if you make this coupling strong enough, you expect to have energy levels that are not equally spaced. And if you even so close to the quantum regime, and this is something very interesting, so it opens many new possibilities to explore new phenomena. So what I propose is to now, because it's for general audience, and so I propose to make a general introduction on mechanical vibrations before to explain more in details my experiments. And so there is a whole zoo of different mechanical resonators. For example, here you have a silicon cantilever that is extremely thin in order to have the resonator sensitive to very small forces. So this is a device that has been fabricated by IBM. Here we have a very interesting structure where here in the middle you have a plate that is suspended, and so the vibrations are localized in this plate because so the structure is suspended, and here on this side what we have is one phonon, so a lattice, a one-dimensional lattice for phonons, so that you have a gap, and so the state here can be localized here. So on the other side you have also this one-dimensional lattice. And so this is important because what is remarkable is these devices, mechanical resonator, is that you can get very high quality factors, up to 10 billion, so 10 to the 10 in small mechanical resonators. So these are extremely coherent systems. This is a graphene resonator. It's a resonator that is only one atom thick. And here what we have is an array of silicon cantilevers with a diameter of about 70 nanometer and that have been grown by chemical vapor deposition. So now what I will do is to explain you why people are interested in mechanical resonators. So 30 years ago or so, nearly no researchers were working on mechanical resonators. And it's only in the last 20 years or so that many people are working on resonators. And I will try to explain you why people are interested. Oh, and I forgot also this very nice system of levitated particles where we have a particle in yellow here that is vibrating in a potential that is created by a focused laser beam, for example. Okay, so why people are interested in mechanical resonators? I will show you a few examples. And so people are very interested to study these vibrations when n, the number of quanta, is on average below 1. Okay? And the state of the art of what has been achieved is to entangle the vibration of this resonator with the vibrations of this resonator. These are experiments that are quite similar to what people have achieved in optics. But there are also some differences. A lot of people are also interested in the question of how well we can detect the vibrations or the position of a system. And there is a limit that is given by quantum mechanics, and it's called the standard quantum limit. And so one way to detect the position very well, as you know, is to use laser interferometry. And this limit, the standard quantum limit, is directly related to the particle wave duality of a laser beam. Because on one hand, you have the wave that you use to measure very precisely the position. But on the other hand, you have photons. So the laser beam is made of photons. These are particles that arrive randomly in time on the system, here on the mirror, and this leads to random forces. So it's shot noise, and this shot noise sets the limit of the detection of the position. So it sets the limit of how well you can, for example, detect events where you have two black holes that merge together, measured in LIGO. Many people are also interested in the mesoscopic physics of these nanomechanical systems. So these systems are very small, and from statistical physics, you know that the fluctuations are larger because the systems are small. Because these systems are small, it makes also that nonlinearities emerge at lower displacements. And also what is interesting is that these systems are a fantastic platform to study far from thermal equilibrium phenomena in a very controlled way, because the quality factor is high and because you can measure the precision, the position with high precision. And so for this reason, many people are working on this. There are a lot of different phenomena, and it's very rich physics. Then it turned out that these resonators are amazing sensors. So you can detect mass that get absorbed on a resonator, or the force that is applied on the resonator. And you can get resolutions here of what this is 1 yoctogram, which correspond to the mass of about 1 proton. And you can get a force sensitivity of here 10 to the minus 21 Newton, which is 1 zeptonewton. And to give you an idea of what this corresponds, this tiny force, it corresponds to the gravitational force between two people separated by a few thousands of kilometers. So we are speaking really about tiny forces. And last but not least, mechanical resonators are also fantastic clocks. So here on my phone, which is in my jacket here, so in every cell phones now, the clocks are made of mechanical resonators, and they're often made by the company C-Time, that is in California. And so here, what I show you is a device that has been cut in two, so you can see the cross-section. And here, this part here, what is called the device, it's suspended and it vibrates left and right like this. And so then you can use this electrode and this electrode to drive electrostatically the system, the vibrations, and detect capacitively this motion. And it's really a nice piece of technology. It costs a few euros, but it's extremely precise, and it allows you to get very precise clocks. Okay, so I come back on the experiments that are carried out in my group. And here in red, we have a carbon nanotube resonator. So the nanotube in red is suspended over the trench. It has a diameter of about 1 nanometer, and it vibrates as a guitar string. The carbon nanotube has a circumference of about 20-40 atoms, so we speak about a resonator with a very small mass. And this is very interesting because the with the pointer, so this the mass, the tiny mass, makes that the zero-point motion here is large. So what is the zero-point motions? These are the quantum fluctuation of a harmonic oscillator. So when you have your harmonic oscillator in a ground state, you have still some fluctuations of the position, and this is the zero-point motion. Okay, so it's something that you have. Yes. Is it an amplitude? Yes, it's in meter. So it's noise. So it's a meter square per hertz.
And is it like an average oscillation or the maximum fluctuation you can get?
That's the variance. So it's and the variance is given by this expression. And the zero-point motion is something very important because when you couple to another degree of freedom, it sets the strength. Okay, and so this guy is very large compared to what you get with other mechanical resonator. And so what is nice is that because the zero-point motion of the nanotube is large, you can couple in a stronger the nanotube vibration to other degrees of freedom. And this is something important, as you will see in my presentation. Nanotubes is quite a mature technology. So you can study Wigner crystal, helium superfluidity, spin physics. You can integrate a nanotube in a superconducting resonator. You can couple the mechanical vibrations of a nanotube with electrons and optical photons. You can do a lot of things. And yeah, so we say that we are able to produce nanotube dream devices. And we say this because we are able to grow carbon nanotubes where there is no missing carbon atom along the suspended region of our device, with essentially no adsorbed molecules on the surface of the nanotube, and with also what is important, the nanotube suspended, and where you have charge fluctuators here and here in the dielectrics, and it's far away from the nanotube. So charge fluctuators is something bad for nanotube devices, electron devices in general. And yeah, so this is our group. So we had a group excursion. It's a fantastic team. We work in collaboration with Fabio Pistolesi on the top right in Bordeaux. So very nice support in theory. Dave Ksaplewski in Argon Lab for support in fabrication, and Andrew Cleland in Chicago for these collaborative efforts towards mechanical qubit. Okay, so I will discuss first an experiment where we have a nanotube that hosts one quantum dot. So the quantum dot is this area in pink. And then what you have is here in gray a tunnel barrier towards this electron reservoir in blue. Okay, so you have an electron reservoir here and a tunnel barrier here. And on the other side, you have also a tunnel barrier and an electron reservoir. And then in the second part of the presentation, I will explain an experiment where the nanotube hosts a double quantum dot. And we can go from one configuration to the other by simply playing with the gate voltages. And in both experiments, I will show you that it's possible to couple the vibrations to the electron in the ultra-strong coupling regime. And I will show you that this is very important to get nonlinearities down to the quantum regime. So you may wonder what is the ultra-strong coupling. So you probably know the strong coupling. For example, between two oscillators, or for example, in this case, the strong coupling between a cavity and a qubit. And the strong coupling is achieved when the coupling strength is larger than the coherence rate of both the qubit and the cavity. Now, the ultra-strong coupling is something it's a more extreme regime. You have to get stronger coupling strength. And then you get new physics when the coupling is larger than the frequency of the cavity or of the qubit, or both of them. And so this is what we reach in our experiments. Okay. Yeah. So we are able to produce a quantum dot by so the quantum dot is here in the pink region. So we have two tunnel barriers, and we get the quantum dot by applying a voltage on the gate here. Because when we apply a voltage on the gate, you see that we have a dot in pink that is electron doped, while here in the blue region, we have the electron reservoir, and you see it's p doped. So we have here, in fact, the tunnel barriers that are formed by the p-n junctions when the Fermi energy crosses the band gap. Okay, so this is the way how we form the quantum dots, and it's we can so precisely control the cis-n. And here, we measure the electrical conductance, so it's the inverse of the resistance, through the nanotube as a function of the voltage applied on the gate, so at the bottom of the trench. And you see a series of peaks. So we work at very low temperature. We work at 15 millikelvin. And in between two peaks, here, we have a constant number of electrons. And in this case, we have 22 electrons in the nanotube quantum dot, and the separation between two peaks in the conductance is given by the Coulomb energy that you have to pay to add one electron in the quantum dot. And now what I will do is to zoom on this peak. And so this is what you get. So here is the conductance as a function of gate voltage. The conductance is 0. Here at the peak, what we have is that the system is fluctuating between the 22 electron state and the 23 electron state. So it's a two-level system, but it's a bit special because the two levels are generating energy. And so at this peak, what we observe is a dramatic reduction of the mechanical frequency. So it goes, when it's not coupled, when the effect of the coupling is cancelled, so you have a frequency near 29 megahertz, and here we can go down to 22 megahertz because of this coupling. And so we have a 21% normalization of the mechanical frequency, which is much larger than what has been achieved in the past. And when we increase temperature, what happens is that this frequency that we measure here at the dip, it will increase. And this is what we observe. So it increases the mechanical frequency. So these are the black squares. And you see that there is a good agreement with the theory of Fabio Pistolesi in red, where and so by comparing the theory to experiments, we get the coupling strength, where you can see that it's 500 megahertz, which is much larger, 15 times larger than the mechanical frequency. So we are deep in the ultra-strong coupling regime. And so here you can see the form of the Hamiltonian to describe the coupling. So this is the coupling strength, this is the displacement, and this is the charge operator. So this strong coupling makes this big suppression of the mechanical frequency, but it also leads to nonlinearities. And see, now here I show you the mechanical response of the oscillator to an oscillating force. And it's nonlinear because the peak is asymmetric. And here, so the horizontal dashed line gives 40 times the 0-point motion. And so this is, this shows that you have nonlinear vibrations rather close to the 0-point motion, much closer than what has been achieved before. So how do we detect the vibrations? We detect them by measuring the current noise through the nanotube. And we use the nanotube as a field effect transistor, and we use the capacitance between the gate and the nanotube. And in this way, we can here measure the noise of the displacement, which correspond to the fundamental mode of the nanotubes, which is at about 90 megahertz. Okay, So now I will explain you my second experiment. And so now in the group, we are working with double dots. Is it different than one dot? The answer is yes, it's very different, because there is one thing that is not nice when you work with one quantum dot, is the fact that the electron has to tunnel between the dot and the electron reservoir in blue. So it goes back and forth, the electron, and the electron reservoir is the bad guy, because it leads to a lot of decoherence and to a lot of losses for the mechanical vibrations. And that's not good if you want to do quantum experiments. And things are different when you work here with two dots in pink, so here and here. And so the electron is tunneling between these two dots, and it doesn't go in the electron reservoir. And things are much better. So in the experiment, we work with a nanotube resonator that can have a quality factor up to 10 million. And so here, the vibrations modulate the electron distribution between the left and the right dot. And you see that here, so that this is nice, because the electron does not go in the reservoir where you have losses. But on the other side, I explained you before that we were detecting the vibrations by measuring current noise through the nanotube. So if we cannot measure the electrons flowing through the nanotubes from this reservoir to this reservoir, we cannot detect the vibration. So we had to develop a new technology, which is to use a superconducting resonator, and that is shown here. So we use radio frequency photons at about 1.5 gigahertz to detect the vibrations. So to summarize here what we are doing, what we have is a mechanical resonator that is coupled to a double quantum dot qubit, which is coupled to the superconducting resonator. And this is the Hamiltonian. So here we have this term that describes the mechanical vibrations. Here it describes the photons of the superconducting resonator. Here we have the electron double quantum dot qubit. And then here these two terms are the two couplings that we have here and here. Okay? And we'll discuss first this coupling. So we have, it's described by James Cummings Hamiltonian, which is used a lot in circuit QED, or in cavity QED, in the last 20 or 30 years or so, and in the dispersive regime. Okay? And so this is interesting because the frequency of the superconducting cavity will depend on the eigenstate of the qubit. Okay? And so you can measure this, and you can know whether the qubit is in the ground state or in the excited state. So this is the device. So the pointer, I still don't understand. Sometimes the arrow is coming out and sometimes not. So the white line that you see here is the nanotube. Here in this region, the nanotube is suspended. And if you look at this device with a larger zoom and with a different angle, you get this. And here you can see perhaps at this level the nanotube that is, but you can barely see it. So don't worry if you don't see it. But the nanotube is here. And we have 5 gates here in order to define the double quantum dot qubit by electrostatic means. Okay? And so in this way, we get 2 double dots. two dots, so in red. And now what I will discuss is what happens when we change the voltage on this gate 2 here and on the gate 4, because this allows us to change the number of electrons in the different dots. And then here, what we do is to measure the conductance through the nanotube as a function of these two voltages. And then you can get double quantum dots here in this region, where here is the electrostatic modulation along the nanotube. You see the band gap of the carbon nanotube that crosses the Fermi energy here. And so this band gap enables us to separate the left dot here from the right dot here. So all this is very well controlled. And we use this superconducting resonator to detect the qubit. And so it took us 3 years to develop this technology in order to have a superconducting cavity with a quality factor that is decent. So we get Q factors above 1,000, which is more than enough for what we want to do. So here, this is where we have the nanotube device. This here is the superconducting cavity. So this where you have radiofrequency photons. And then we use this aluminum bond wire here to couple the two systems. And it allows us to get a superconducting resonator with frequency at about 1.5 gigahertz, so within the bandwidth of the filters that we have in the cryostat, and with a quality factor that is typically above 1,000. This is what we can achieve. Okay, so I told you that we can use this V-gate 2 and V-gate 4 to change the number of electrons in the two dots. And here what I show you is that it's possible to move the electron from the left dot to the right dot here. Okay? So we move the system along this red line by playing with these two gate voltages. And when this red line intersects here the green line that we measure, we have that the left dot, we have that the left dot and the right dot that are in resonance. So we have the potential of the two dots that are in resonance. The two dots hybridize, and then it creates a qubit. And here, I show you the tuning, which is the energy difference between the left dot and the right dot. And so when it's 0, here it's when we have the resonance between the left and right dot, and then the qubit frequency is given by the couplings, the tunnel strength, sorry. So the tunnel strength here. And we can measure the qubit here by measuring the frequency of the resonator. And you see here a reduction of the frequency of the superconducting resonator. And from this reduction, we can get the tunnel coupling that is equal to 11 gigahertz. So from this simple expression. We can also tune this tunnel coupling with the gates. So here it's possible to change the frequency from 2 gigahertz to more than 9 gigahertz here in this plot, but we can go above 100 gigahertz. And this is because when we play, for example, with gate 3 here, it's possible to change the position of the band gap with respect to the Fermi energy, and in this way you can change the tunnel coupling. So we have a system that we can control very well with the different gates, and where we play with one electron, we can play with the tunnel coupling, and then we couple this to the photons of the superconducting resonator. Okay. So now I would like to finish by discussing the most important part of the experiment, where we couple the mechanical resonator to a double quantum dot qubit. And what we get is that the coupling is larger than the mechanical frequency. So we are again in the ultra-strong coupling regime. We use the superconducting resonator to measure the mechanical vibrations. And in fact, when we drive very strong the system, we can detect all the mechanical modes, almost all the mechanical modes. And this is what is shown here. So here we have the fundamental mode of the vibration, where here I show you the shape of the eigenstate. Then here we have the next mode with the eigen shape given by here that is shown here, and that where you have one node. Okay, and then you have two lines because you have the two polarization, parallel and perpendicular. And so what is interesting us is this mode here, because you have here one node, and you see that along the nanotube. So it's the mode here. It corresponds to this nanotube that is going up and down. So that's the shape of the eigenmode, and you see that it's very symmetric compared to the double quantum dot, and because of this, you have the strongest coupling strength. Okay, so for this reason, we choose this mechanical mode. And we observe a dramatic reduction of the mechanical frequency when we tune the energy difference between the left and the right dot. And from this reduction, we get a coupling strength that is larger than the mechanical frequency, so that we are again in the ultra-strong coupling regime as for the first experiments that I discussed. Okay, so what we can do also is so that's the Hamiltonian. We can diagonalize the Hamiltonian, and here what I show you is the energy, the potential to be more precise, of the system when the qubit is in the ground state. And here you can see that we have the x squared, so this is the harmonic potential. This term here, it's the suppression of the mechanical frequency that I just discussed. And that's what is even more interesting is this term. So it's the nonlinear term. It's the Duffing term for mechanics, but it's exactly the same as the Kerr term in optics. And what I've just shown you is that the coupling strength between the electron and the vibration is strong. And this makes that this term here is very large. And so that's the interesting thing. Okay. So we use the resonator, the superconducting resonator, to detect the vibrations. And so we have here a direct relation between the displacement of squared with the cavity frequency. And so again, so what is interesting is here the coupling strength that is large, and this makes that we are able in this way to detect vibrations even in the quantum regime. So when the displacement is smaller than the 0-point motion. And also what is interesting when you look at this is that the observable, so the shift of the cavity frequency is proportional to the displacement squared, which commutes with the Hamiltonian of a oscillator. And so this makes that you have in principle a QND detector, so quantum non-demolition detector. So the back action is significantly reduced. And so these are the measurements. So these are the last measurements that I will show. So here is the response of the oscillator to an oscillating force. So we drive here, we sweep, sorry, the frequency of the oscillating force. And you see that the peaks here are asymmetric. So these are peaks measured with different forces and for different colors. And you see that they are symmetric, so these are nonlinear vibrations. What you can see also is that the mechanical frequency goes up, and this is exactly what you expect from a Kerr or a Duffing oscillator, so a nonlinear oscillator. And then here, what I show you, it's the mechanical frequency that we observe. So for different forces, so for example, here we have a mechanical frequency here, so the resonance frequency here, and then we have also then the displacement from this axis that I plot here. And you see here is, for this point we have because here it's so here it's a signature of nonlinearity, so it shows here that for when we have displacements that are 10 times the 0-point motion, it's highly nonlinear, and it remains nonlinear down to the level of the 0-point motion. What we have also is there's the slope, and this slope is consistent. Well, there is a factor 2 difference, but it's close to what is expected from the Hamiltonian that I have shown you before. Okay, so with this I would like to conclude. So in the first experiments, I've shown you that it's possible to couple the vibrations to the electron in a one quantum dot in the ultra-strong coupling regime. And I've shown you that this is essential to create strong nonlinearities for vibrations that get close to the quantum regime. And so in this experiment, first experiment, we reached these points. And so here, so this is this axis to show you how close we are from having nonlinear vibration in the quantum regime. And so here, when you reach this level, so when this is 1, this is when you have nonlinear vibrations at the 0-point motion. So the first experiment, we reached this. And then the second experiment with the double dot, we reached this point. So we are we see nonlinearities at the 0-point level, And I would like also to emphasize that the group in Zurich got very similar results, and it was published last week in Science. Okay, so in conclusion, well, in outlooks, what can we do? So we have a lot of things to do, fascinating phenomena to explore. For example, we would like to demonstrate a qubit that is mechanical with enhanced coherence. So compared to what has been achieved with qubit in mechanical system, in quantum matter systems. What we want to do also is to study the quantum bifurcation to a double well potential. So it's like a quantum phase transition in condensed matter where you tune one parameter. And so here you can go for, vibrations as described by a harmonic potential typically. But so what you expect with the system that we have is to go in a regime where you have a double well potential for the vibrations. And so this is, you get like a quantum phase transition from the single well to the double well. And has never been measured. It will be really an extreme nonlinear physics, nonlinear system that has never been measured in physics. And it will allow you, for example, to make crazy states. So, for example, Schrödinger cat states in the ground state. So if you think about this, it's crazy. It may enable us to also to develop new squeezing protocols without any parametric drive, which, from what I know, have never been done. But what is really motivating us the most is the last thing, which is to demonstrate non-Gaussian states with large delocalization. So in other words, it's to demonstrate microscopic quantum superposition states. So perhaps you know the work in Vienna from Marcus Arndt, and it has been started when he was working with Zeilinger, and where they were using this double split experiment of Young to send photons and then to look the interference after they go through the double slit experiment. But so what in Vienna they have done is to use not photons, but molecules up to 10,000 atoms. And they show some quantum interference, so it's, it becomes more macroscopic. But for them, it's very difficult to go to show such macroscopic quantum superposition states in systems that are larger. So they have now to go in space for this. And so here, with the system that we have, theorists say, it's a very interesting system to explore such quantum superposition states in a system with a larger mass. So our goal in the lab is to demonstrate a quantum superposition state with the quantum delocalization that is larger than the diameter of the nanotube. It's not very spectacular at first sight, but it shows it would open a new path in demonstrated quantum superposition states in large systems. And with this, thank you for your attention.
From somebody online, what is a quantum dot? Somebody asked.
What is a quantum dot? A dot is, the word dot is used because it's a point. And so it's a zero-dimensional point. So it's Y. And then, so typically in condensed matter, a quantum dot is used because you have atoms together. And so you can have an electrons, but then the electron is delocalized, is confined in this quantum dot. And so because of the spatial confinement, you have some quantization in energy. And on top of this, you have also to pay the Coulomb energy when you work with the devices that we are using because when you add one electron, you pay the confinement energy plus the Coulomb energy.
Thanks a lot for the talk. I was curious, I am a bit confused. I don't really understand how the special shape of these nanotubes are related with localization of these two quantum dots that you have. How are the mechanical oscillations and the amplitudes kind of isolating both probabilities of finding the electrons?
Okay, so should I answer here? Yeah. Okay, so I'm not. So I will try to answer you. I'm not sure if it will answer to your question. But so what we have is that the electron. So what we have is that the electron. So we have two dots along the nanotube, and then you have the two levels of the two quantum dots. And so when they are in resonance, the one electron is delocalized between the two dots. Okay. Now what you can do is the vibration. What it will do, so this mechanical mode, is that you have the two levels. They will modulate like this. So because of the vibration, so because of the capacitive coupling, you have then this modulation. And so you can see here. So what it will do is that. There is a new dynamics.
Because the cloud probability density is localized around the nanotube?
Yes, along the nanotube, yes.
Okay, yeah. I think that clears my question. Thanks.
So thank you very much for the presentation. I'm just curious because you've talked a few times about noise. I would like to ask you what is the meaning of noise when you have the oscillation of the electron between the two quantum dots? Do you have noise over there or? Because, I mean, can you measure the noise of the system in terms of the probability of localizing the electrons somewhere? Or?
So can you repeat the questions? Because I'm not sure to understand.
Yes, you've talked about noise in few slides.
Yeah.
So I'm just curious to understand what is the meaning of noise when you have the electron fluctuating from one state to the other. It's
delocalized.
Uh-huh.
So the electron, so the wave function. So you have a wave function, and then you have a certain probability to be on the left and on the right. Then I'm not sure how to do then a noise measurement of such a system. You have to do so because so with electrons, so usually so you can think in two types of noise. You can think in the Johnson-Nyquist noise and on the shot noise. But here, so the Johnson-Nyquist noise is, it's the thermal energy related to Brownian motion. And but then you have also the shot noise where you have a current flowing. But so here, so there is no current flowing through it. So there is no.
So that's the point. Can you hear the noise of the fluctuation of the electron probability, or not?
So can you measure the noise? So I don't see how.
So that was a curious.
Yes, I would like to ask something myself. I suppose the quantum, the nanotubes have to be very clean. I mean, very often the nanotubes have some molecule added.
Yeah.
And how do you, and the added molecules, so atoms should change the frequency of everything. And how do you prepare the nanotube? Yeah. How do you prepare?
Yeah, so what we do is, so we make many devices, and then we select devices where the resistance is below 50 kilo ohm at room temperature, because when you go to lower temperature, the resistance usually does not diverge, and this indicates already there is no missing carbon atom. Because otherwise, if there was a missing carbon atom, you would have a resistance that diverges because you have a 1D system. Now, about the molecules that are absorbed on the surface, so what we do, because when you have the nanotube, you transport the device in air, so molecules would get absorbed onto the nanotube. But what we do is that when we are in the dilution fridge at 15 millikelvin, we pass a high current through the nanotube, and then we remove it. And we can show that we remove these adsorbed molecules by measuring the resonance frequency, because we were able to make monolayers of helium atoms, so 1 layer, 2 layers of helium superfluidity. And it was matching, so by measuring the vibrations, we can measure the mass, so we know exactly how many atoms of helium we have with respect to of those of nanotube. And so our experiments were indicated there within the area of our measurements, we cannot identify extra atoms than the one of the helium and the one of and those of the nanotube. So it's why we claim that we can essentially remove all the atom molecules and atoms.
Thank you. Now I understand. And another question is, thinking, probably you have thought about the possible applications. Thinking on applications, it should be related to applications on quantum computing?
Well, yeah, so there is the quantum computing, so it requires to make a circuit where you position nanotubes in a very precise way. It's difficult, but it's something that is done in a startup company in Paris, C12, where they got a lot of money for this. So it's hard work. It's difficult to position the nanotube where you want, but let's see where they are able to go. In our case, it's not our goal to make a quantum computer because of this challenge that is difficult to tackle, and you need a big team to do this.
Okay, thank you. Let's see if somebody else asks something. No, I cannot see more questions. So in that case, thank you very much.
You're welcome. Thank you for listening.